Okay, our last section is 14.5. We're going to do your favorite word problems, but we're going to do what's called actually related rates. It's kind of using the idea of implicit differentiation that we talked about in the last section, but with more application problems. So when we did implicit differentiation in 14.4, we talked about how y was changing with respect to x. And so when x is 4, what is the rate of change in y? When x is 5, what is the rate of change in y? But things in life aren't always just x's and y's. A lot of times, situations in life change as time changes. And so we want to find the rate of change, but with respect to time now instead of just x's. So when we find, let's say, the rate at which volume is changing over time, I can say dv dt. Or if I want to talk about the rate at which my cost is changing over time, I can say dc dt, the rate at which my cost is changing, but with respect to time instead of quantity or something like that. Lots of different situations, but today we're going to talk about what happens when things change, finding the rate of change with respect to time. Okay, it's called related rates. That means anytime we find the derivative of x with respect to time, we have a dx dt now. Anytime we find the rate of change of y with respect to time, we do a dy dt. Anytime we're finding a rate of change, we're finding the derivative, but with some of these problems, we're doing it with respect to time. Okay? All right, the first example we're going to do is kind of still just a very generic example with x's and y's, but we're going to do some more examples here in the next few videos that are a little bit more application. But I wanted to start with this one first. It says, suppose that x and y are both functions of t, which can be considered to represent time. So we're going to figure out the rate at which x changes over time and y changes over time. And that x and y are related by this equation. Suppose further that when x equals 2 and y equals 3, well then dx dt equals 13. We want to find the value of dy dt at that same exact moment. So time's going on and all this stuff is changing. If you stop the clock, when x is exactly 2, y is exactly 3, and dx dt is 13, can we find dy dt? Okay? So what we have to do is find the rate at which all this stuff changes. And we know that the rate of change is really just the derivative. So what we need to do is find the derivative of this equation. Okay, making sure that you find the derivative with respect to time. So when you find the derivative of x, you add your dx dt. When you find the derivative of y, you add a dy dt. For this first term, you have an x times a y squared, so you should be using product rule. Remember, anytime you take a derivative of x, you do a dx dt and y dy dt. Let me show you. So I did the first, x, times the derivative of the second, which is y squared. So the derivative of y squared is 2y with a dy dt. Plus the second, y squared, times the derivative of the first, which is x. So the derivative of x is 1, but I need to make sure now that I add a dx dt. I'm going to find the derivative of y, which is 1 dy dt, equals the derivative of x squared is 2x dx dt, and then the derivative of any constant always is just 0. So that's why there's nothing there. Okay, go through that one more time, process that, make sure you understand it if you need to before moving on, okay? All right, from now I'm going to simplify that a little bit, make it look a little bit nicer with less parentheses, with leading coefficients, stuff like that. And then in the problem, remember it said when x is 2, when y is 3, and dx dt is 13, we want to find dy dt. So what we want to do is plug in our information that we do know so that we can find out what dy dt is. So it looks like here I solved for dy dt. So in my equation, my dy dt was in this term and in this term. So I kept both of those to the same side. I moved everything else to the other side, so I moved this y squared dx dt to the other side by subtracting it. Since the two terms that I had dy dt's in them had a dy dt, I GCF'd that out. That left me with a 2xy plus 1, because there's an invisible 1 here, on the left side. On the right side, I have my 2x dx dt minus y squared dx dt. And again, in the problem, it tells us that when x is 2, y is 3, dx dt is 13, we want to find dy dt. So I should be able to either divide and then plug everything in, or I can plug everything in now. So it looks like I took this and I plugged everything in right away. Again, remember in the problem that it says that x is 2, so that's where this 2 came from. Oh wait, this 2. The first 2 came from the 2 that was already there. This 2 came from when x equals 2. It says that y equals 3, so that's where I got those values from. Here's a 2, x is 2, dx dt, remember, is 13. Y is 3, and dx dt again is 13. So then I just used my math. I multiplied all these pieces together, squared, multiplied, subtracted, and then I divided by that 13, which is on the other side. So we end up getting that dy dt is equal to negative 65 over 13, which happens to actually be negative 5. What that means is that y is changing at a negative 5 rate as time changes. Okay, so at this moment that they stop the clock, y is changing at negative 5 whatever per second. Right? There is no units on this example. It's just kind of generic, but that's kind of what it would mean in an application problem. Okay? Make sure that you do that example, which is the basics, because here in the next few examples, next few videos, we're going to add a little bit more application to it. Okay?